In analytics, very often we end up studying the relationships between two numeric quantities. For example, if we were in sports analytics and we were interested in studying the number of wins that a college football team accumulated over the course of a season, we might study the relationship between the number of wins and, let's say, the number of fumbles lost over the course of a season, the number of passing attempts, the number of rushing attempts. If we were trying to develop baseball analytics, the origin of Moneyball, you'd be interested in what makes teams win. So what characteristics of players are associated with teams winning? Is it the player's on-base percentage? Is it their batting average, the number of home runs? If you're working for a college admissions department, you'd like to know who are the best admitted students. Who do you want to be putting into your college? So you might study the relationship, let's say, between the college GPA and their high school GPA, or maybe their ACT or SAT scores. Or you might be looking at other factors that you know about them in high school, like the number of sports they played, the number of extracurricular activities they had, and how that's associated with their ultimate college GPA. Or if you're working in marketing analytics, you might be interested in studying consumer spending. How is the amount of money that people are spending, let's say at Trader Joe's, associated with the amount of money that they spend at Shoney's? Or if we're releasing a new product, how strongly does the first week of sales predict, let's say, sales 10 weeks into the future? And customer analytics is a big focus in the business school. Is there an association, let's say, between a household's income and the frequency of purchases or the purchase amount at Amazon.com? Or if you want to do some pet analytics, you might want to study the association between how hot it is outside, the temperature, and how far your dog can walk before ultimately getting tired and just refusing to go any further. Now, the first thing that we do when we study the association between two numeric quantities is to make a scatterplot. Because what we see in the scatterplot is going to guide us into whether we use Pearson's correlation, which you learned last time, to gauge the strength of the relationship and to do statistical testing, or if we need to use Spearman's rank correlation in order to gauge the strength and to do the statistical testing. So a quick review of when Pearson's correlation is appropriate. When we look at the scatter plot, if we see a stream of points whose shape is well described by a circle, an ellipse, a vertical band where the trajectory is linear, there's very few outliers, and the point cloud is homoscedastic, meaning that the vertical spread up and down is about the same everywhere you look left to right. When we have all of those things, Pearson's correlation shines when it comes to describing the strength of the relationship and then also doing statistical testing. However, if we look at the stream of points and we see noticeable nonlinearity, that's going to be a clue that Pearson's correlation is not going to cut it. We'll need Spearman's rank correlation. Or when we look at the scatter plot and we see heteroscedasticity, where the vertical scatter in the stream of points changes as we look left and right. If it gets thicker for larger values of x or maybe thinner for larger values of x, Pearson's correlation is not going to cut it. We need Spearman's rank correlation. Or if we look at the scatter plot and we see extreme clumps of outliers, we know Pearson's correlation is not going to be useful. It's too affected by those few outliers to really give us much insight, and so we need Spearman's rank correlation instead. So first, let's look at some examples where Pearson's correlation is going to do a great job at quantifying the strength of the relationship. So we would actually use the term that these two variables are correlated with each other rather than the more generic term that the two variables just have an association. So I'm going to load up a few of the data sets that we've been using for this course. And the first thing that I want to look at is the relationship between someone's math score and their reading score on a standardized exam. So we look at this stream of points and we see that the trajectory is well described by a straight line. The overall shape of the stream of points is well described by an ellipse, and there aren't any major outliers, so we know that Pearson's correlation indeed is going to do a great job at capturing the strength of the relationship. And so we could look to see if we do have a statistically significant relationship by running the associate command. Likewise, if we were to go and look at the ratings left for different types of ice cream, the number of stars between 1 and 5, and the sentiment of the review, the text review that people have left, we see a nice positive correlation going on between these two quantities because the trajectory of the stream of points looks like it's well described by a straight line. There aren't any extreme outliers. We don't see any curvature. And so we're in a place where Pearson's correlation is what we would use to describe the strength of this relationship, and we could run associate to determine if we do have a statistically significant relationship here. As another example, we could look at the rents that people were paying in cities in January 17 and 6 years earlier, January 2011. The trajectory of the stream of points is well described by a straight line. The overall shape is pretty well described by an ellipse. We do see some outliers at very large values of these rents, but these outliers aren't too extreme and they're outnumbered, I would say, by the normal rents that we have in the data set. So I would say that correlation is still a good measure to quantify the strength of this relationship, and we could do the statistical testing consistent with that. If we had doubts, well, we can implement the procedure we'll introduce today using Spearman's rank correlation. And finally, if we look at the example, let's say from baseball, where we look at the number of wins that a team has over the course of a season versus the typical on-base percentage of that team, we see a stream of points that's well described by an ellipse. The trajectory is nice and linear, well described by a straight line. There's no extreme outliers. Once again, Pearson's correlation is going to be the metric we would use to quantify the strength of this relationship and to do the statistical testing. So let's talk about some scatter plots that would indicate that, nope, we need a different approach. Pearson's correlation is not going to cut it. So for example, if we were to look at the chemical characteristics of different wines in the EX6 wine dataset, here we're looking at the relationship between the density of a wine and its free sulfur dioxide content. And you notice that for the most part, this stream of points is well described by an ellipse and it has a linear trajectory, but we do have a few extreme outliers that are very far separated from the rest of the stream of points. And even a single point, when placed in just a bad location, can really ruin the analysis that Pearson's correlation provides. And so in the presence of these extreme outliers, we would like an alternative. And we'll be using Spearman's rank correlation to help us out. Likewise, if we look at the relationship between the balance that someone has at a bank and the credit score of that person, we find a stream of points that looks roughly elliptical. Kind of the trajectory is well described by almost a flat straight line. But we do have some weird outliers, a bunch of people in the data set with just no money in their account, and a bunch of people with perfect credit scores off at the far right. This is a clump of outliers that don't really fall in line with the rest of the stream of points, and with this many outliers, we'd be wary to use Pearson's correlation to capture the strength of the relationship. If we look at the relationship between the sale price of a bulldozer and the year that it was made, we see that the stream of points is very clearly nonlinear, kind of tilting up and to the right here in a nonlinear fashion. And so we know Pearson's correlation is not going to help us out here in terms of quantifying the strength of the relationship or doing any sort of statistical testing. We need the backup of Spearman's rank correlation to help us out. Also, if we were to look at the price of a diamond versus the number of carats of that diamond, we see that the stream of points actually has a lot of issues when it comes to trying to quantify the strength of the relationship. First, the trajectory is highly nonlinear, it's highly curved, and then also we have tons and tons of outliers at very large carats. And it kind of looks like that the stream of points is split up into a couple of vertical bands. There's just a lot of really weird features. So we know Pearson's correlation is not going to help us out here. We need an alternative, which is going to be Spearman's rank correlation instead. As a final example, let's look at the sentiment scores of text reviews left for Disneyland theme parks versus the number of words in those reviews. Here we see an example of heteroscedasticity, where the vertical scatter in the stream of points is not the same everywhere. So to use Pearson, we need to have the stream of points basically look like a tilted band. And here we see the band's thickness is highly variable depending on the number of words. The band is very, very thick for low numbers of words. And as we look at reviews with more numbers of words, that thickness gets smaller and smaller. So we have unequal vertical spread, we have that heteroscedasticity, and so we know that Pearson's correlation is not designed well to gauge the strength of a relationship in this case. We're going to have to use our backup, which is Spearman's rank correlation. So when Pearson's correlation is not going to be an appropriate measure of the strength of the relationship, we have nonlinearity, we have outliers, we have heteroscedasticity. What's our alternative? Well, what we're going to do is explore ranked-based correlations as alternatives, and this is kind of a cool trick of what we can do with the collected data values. So once again, our process when doing this analysis is to look at the scatter plot and to determine, are we going to be quantifying the strength of this relationship with Pearson's correlation, or do we need an alternative, Spearman's rank correlation? What we'll do is we'll still run associate, we'll just make sure to look at the appropriate line of output. So, how does Spearman's rank correlation work? Well, it actually takes the original data values and performs kind of a cool trick to perform the analysis. What it does is it looks at the original data values and replaces those original data values with the ranks of how big or small they are in the data. So, for example, in our column of X here, we have 3.1, 2.4, 5.2, 7.1, and 0.3. And what we're going to do is replace those values with their ranks. So 0.3 is the smallest data point in the data set here. It gets a rank of 1. The second smallest value, 2.4, we're going to replace that 2.4 with a 2. The third smallest is 3.1. We'll replace that with a 3, so on and so forth. In our Y column of data values, we have negative 1.3, 2.3, 0.3, 6.5, 1.7. Well, the smallest value in that data set is minus 1.3, so we'll replace that with just the number 1. The second smallest value, 0.3, we'll replace that with just the number 2, so on and so forth. And then what we're going to do actually is just do a standard Pearson's correlation analysis just on the data set of the ranks instead. So essentially, instead of analyzing the data values that we've collected, which we can always do, we know as business analytics practitioners we have a choice of what we actually analyze. Here we've just replaced the data values with their ranks and just proceeded with a normal Pearson's correlation analysis here. So let's look at a few examples where we have to use Spearman's rank correlation when we use the associate function. So first, let's look at the relationship between the density of a wine and its free sulfur dioxide content. We saw that this had some pretty extreme outliers, so we knew that Pearson's correlation was not what we were going to use to quantify the strength of the relationship or to do the statistical testing. Instead, what we'll do after running associate, we'll scan up and find the row that says Spearman's rank correlation, and we'll do the analytics based on what we find for this row. So the value of Spearman's rank correlation is about 0.3. It's positive, so above average values of density are typically found with above average values of free sulfur dioxide. Below average values of density are typically found with below average values of free sulfur dioxide here. So it's a positive relationship. And what we're measuring is a value of 0.3. It ranges between -1 and 1, so this is a moderately strong relationship here. So unlike Pearson's correlation, we don't really square this and interpret accordingly. We just look at the value of the correlation, we appreciate how far from 0 it is, and then we ask ourselves, okay, well, is this a statistically significant relationship? So we scroll down and we find the p-value of Spearman's rank correlation, and in this case we find that it's somewhere between 0 and 0.007. Since all those values are less than 0.05, we can say that yes, this is a statistically significant association. And looking at the scatter plot, it looks like it's a reasonably strong one to help guide us in terms of what we know about density and free sulfur dioxide. Knowing the free sulfur dioxide narrows down to a decent degree what the density content in that wine might end up being. Let's look at another example here, the relationship between the balance of someone's bank account and their credit score. So this was a stream of points that looked very elliptical, but had these huge clumps of outliers, a bunch of people that had zero balance, a bunch of people with perfect credit scores. So once again, with all those outliers, we know that Pearson's correlation is not going to help us out. Instead, what we'll do is we'll look at Spearman's rank correlation. Now, it's an extraordinarily small value. It's so close to 0 that really for all intents and purposes, these values look to be nearly independent. In fact, if we look at the p-value of Spearman's rank correlation in this case, all the values are above 0.05, so we can actually say that there's no statistically significant association between these two quantities. What about the sale price of a bulldozer and the year it was made? Well, let's actually go for brand new bulldozers here. So bulldozers with usages fewer than 300 hours here. If we just restrict ourselves to bulldozers with that little usage, we find there's only a couple bulldozers in our data set. But what we find is that the relationship from before was a bit curved. So we know that we want to be using Spearman's rank correlation here with a nonlinear relationship. And so we go when we look at Spearman's rank correlation, it's a value of 0.6. So a fairly highly positive association going on. The more recent the bulldozer was made, the larger the year made here, typically the higher the sale price. Is this a statistically significant association? Well, if we go and look at the p-values, what we find in this case, the test is inconclusive because we see that 0.05 is smack dab in the middle of the range of estimated p-values that the test is giving us. So what's our recourse? Well, all we have to do is to up the permutations argument in associate. So if we copy and paste our command and go ahead and add in an additional argument, permutations, and bump it up to some large value, maybe like 5,000. The default is 500, so you want to make sure it's bigger than 500. It'll go through and with more permutations, the more accurately we've estimated the p-value, and now we've pretty conclusively established that yes, this association is statistically significant when we consider bulldozers whose usage is smaller than 300 hours here. Another example, if we look at the association between the price of a diamond and the number of carats, we see it's a highly nonlinear relationship with lots and lots of outliers. Pearson's correlation not going to be useful here, so we use Spearman's rank correlation instead to quantify the strength of the relationship and to do the statistical testing. And what we find is Spearman's rank correlation is almost a perfect one, 0.96. So these are highly associated, extremely tightly connected together. Knowing the carat of the diamond informs you greatly of the possible prices of that diamond. Spearman's rank correlation says that there's a very close correspondence between these two quantities. Is it statistically significant? Well, you bet. If we look at the p-values that have been estimated from the test, they're all well below 0.05, between 0 and 0.007. And so this is a highly statistically significant relationship. Diamonds with more carats typically sell for more, have a higher price, but in a nonlinear fashion, kind of a curved fashion here. And then finally, if we look at the relationship between the sentiment of a text review that's left for a Disneyland theme park versus the number of words, we saw that we had a heteroscedastic relationship. The vertical scatter wasn't the same everywhere we looked. This isn't as simple as a tilted band. We had huge scatter for small numbers of words, little scatter for large number of words here. We know that Pearson's correlation is not designed to help us out, and so instead we're going to look at Spearman's rank correlation, and we find that there's a negative correlation. So reviews with above average number of words tend to have below average sentiment values, and reviews with smaller than average number of words tend to have above average sentiment. So is this statistically significant? Well, it sure looks like it is because the estimated p-values are all between 0 and 0.007, all less than 0.05. So we have a statistically significant association. Let's wrap up our discussion of Chapter 2 with a discussion of the permutation test, which we've been using all along to gauge whether or not our association is statistically significant. So remember our procedure. We go and look at the estimated p-values, and if those p-values are less than 0.05, we say that the association is statistically significant. In other words, there's a very small chance that we would have observed an association at least as strong as what we measured in the data by random chance. In other words, just by chance alone when we go and collect data when there's really no association going on between the two variables in study. So that poses the question, well, how do we know what values of the correlation, the discrepancy, might we observe just by random chance? And that's where the permutation procedure comes in. So let's talk about this. So let's imagine that we had a data set with two columns, x and y. X just contains the integers 1 through 5, and y contains some other values here. So in our original data, we might measure Pearson's correlation, and it could come out to be 0.94, a pretty strong correlation. Now, we need to ask ourselves, could this 0.94 been produced just by random chance alone? If x and y were completely unrelated, and we went and collected some data, we know there's a lot of randomness inherent in the data collection process, could we have observed a correlation at least as strong? So here's what the permutation procedure does. It preserves our original x values when creating a new permuted data set, and the y values are simply a reshuffling of the collected data values we've already seen. So in permutation data set number 1, maybe the first y value is now 4.4, the second y value 6.0, 5.6, etc. If we shuffle up the y values and randomly assign them to the x values, then by definition we know that x and y are completely unrelated. So when we go and measure Pearson's correlation for this permuted data set, we're going to get a value that's literally being produced just by random chance, or the randomness inherent in the data collection process. By design, x and y are unrelated, so this value of r of minus 0.69 for the permuted data set number 1 is a value that's being produced by chance alone. And then we repeat this procedure. We shuffle up the y's once again. We randomly assign them to each value of x. We measure Pearson's correlation, and this is going to be another value that's been recorded just by chance alone. X and y are unrelated because we've randomly assigned the values to each other. There's no association going on. So in the second permuted data set, this correlation of minus 0.54 is something that's being produced just by random chance. Permuted data set number 3, same sort of procedure. Shuffle up the y values, randomly assign them to the x values, measure the correlation, and so on and so forth. We'll repeat this, and by default, Associate does this a total of 500 times, until we have 500 values of Pearson's correlation that have legitimately been produced by random chance, where we randomly assign the x values and the y values together. And so when we look at Associate and we look at the very bottom set of plots, regardless of y or x is categorical or numerical, that's essentially what we're seeing. The red vertical line is going to tell us the observed value of our measure for the strength of the correlation. Pearson's correlation, Spearman's rank correlation, the discrepancy between observed expected counts, the F statistic if we're comparing averages, the discrepancy if we're comparing medians, all same idea here. The red vertical line is going to tell us the observed value from our original data, and then the histogram is going to show us the values that could be produced by random chance when this permutation procedure is run. And so to establish that the association is statistically significant, we need to show that what we measured in our data is very unlikely to have been produced just by random chance. In our example right here, we found the observed correlation in the data was 0.94. Is it possible to observe that value just by random chance alone? Well, yeah, occasionally we do see correlations of at least 0.94, or more negative than minus 0.94, at least as strong as the value we observed, positive or negative here. But it turns out that if we look at all of our permuted data sets, this turns out to be a fairly rare occurrence. Only 2% of those permutations resulted in correlations that were at least as strong, positive or negative, as the value we measured in our data. And so this is what we call the p-value, the probability that random chance alone is able to produce a correlation or an association at least as strong as what you measured from your data. Since this is less than 0.05, we would say that this is statistically significant. So for an example, visually at least, how the permutation procedure works, let's look at some NFL data. So let's let my y variable be the number of wins over the course of a season, and let's let x be the offensive pass yards per attempt. So how many yards is the team getting on offense when they attempt to pass here? Now, if we make a scatter plot of this association, we find that Pearson's correlation would be appropriate for measuring the strength. The stream of points looks nice and elliptical, like a tilted band. There aren't any extreme outliers. Nice linear relationship, and I've added a trend line just to highlight that the trajectory really is linear. So if we measure the correlation in the data that we've collected, we find the correlation is about 0.6. So squaring that, about 36% of the variation in the number of wins over the course of the season can be attributed to differences in this metric, the number of offensive pass yards per attempt. The other 60 or so percent must be due to other factors that might be in the data. And this is a pretty strong correlation. And so we'd like to know, is this statistically significant? Well, let's go and observe what sort of correlations we might see just by chance alone. So what I'm going to do is I'm going to preserve the x values that I've observed in the data set, and I'm going to randomly shuffle up the y values with the sample command. Sample, give it a name of a vector, and it'll randomly reorder the values in that vector here. And so by definition now, x and y have no association whatsoever. They're kind of being randomly paired up with one another. And so when I make a plot of the values in this permutation data set, that trend line essentially disappears, kind of indicating that, there's no trend going on here. This is a scatter plot I would observe if there's no association going on between these two variables. What if I were to go and actually look to see what's the correlation in this permuted data set? A correlation of 0.02. And if I were to run this again, correlation of 0.045, 0.056, these are all values that I'm observing by chance alone because I'm randomly pairing my x and y values together. And so after we do this a few hundred times, maybe a few thousand times, we've built up a collection of correlations that are being produced by chance alone. And so we can compare that to the correlation we observed in our data. And we're finding that this 0.6 is actually really quite impressive. We never saw anything remotely close to a correlation that strong when we were randomly pairing the x's and y's together. And so when we run associate, and we run this on the original data here, we've got that scatter plot, and here are histograms of those values of the correlation that we're observing over this permutation procedure. These are the values that we observe by chance alone when x and y are completely unrelated to one another. The red line indicates the observed correlation in our data set, and so we can see just how out of whack that measured correlation is with what could be produced by chance. So we've essentially established that this is going to be statistically significant. There's no way chance alone can produce a correlation at least as strong as what we're observing in the data. And indeed, if we were to go and look at the p-values of the correlation, we find they're all much less than 0.05. Yes, this association is highly statistically significant. And this procedure is the same regardless of whether x and y are categorical or numerical. If we go back to the Cuss loyalty dataset, we might be interested in looking at the association, say, between the marital status and the income level of a household. So we have single households, married households, and then the income levels of these households. We see some differences in the conditional distribution, the marital status, as we go from one level of income to the next, but not a huge variation. So if we go and measure the observed value of the discrepancy between the, say, observed and expected counts in our data. So here's what we observed in the data here. Here's what we expected to see in those cells if there is no association. We see a reasonably sized discrepancy between the marginal distribution of marital status, what we observe in the data set overall, and the distributions for each one of the 6 levels of income. So we see some discrepancy going on. Our numerical value is 5. Our question becomes, okay, well, is a discrepancy of 5 something that could be produced just through the randomness inherent in the data collection process, or is this discrepancy of 5 indicative of a association going on? So what we do, we randomly pair up the x and y values, we measure the discrepancy for those permuted data sets, and after the course of 500 permuted data sets, we get a nice histogram of the values of the discrepancy that arise just by chance alone. The vertical red line tells us our measured value of the discrepancy, and so we just ask, okay, well, what's the probability that chance alone could have produced a discrepancy at least as large as the one we observed in our data? So what fraction of discrepancies in these permuted data sets are at least as big as what we observed? Well, that's where the 37.2% comes from. And so what we do is we look at the confidence interval for that p-value. It's somewhere between 0.33 and 0.416 after 500 permutations. We've nailed down the p-value reasonably well, but there's still a little uncertainty with it. Since all those values are at least 0.05, we know that this association is not statistically significant. If we were to compare the first purchase amounts of customers to a store versus their income, we can see the box plot showing that there's a little bit of a variation in the averages or the medians here. If we were to compare the average first purchase amount, which looks reasonable to do, the QQ plots look pretty good here. The trajectory of the stream of points pretty close to that diagonal line. What we would find is that, okay, we do observe a difference in averages here across those 6 different income levels here. And if we were to look at the value of the discrepancy, we get a value of 0.345. That's our summary of how different the averages are from one income level to the next. So how often do we see discrepancies at least as big as this when we randomly pair our x and y's together, those income amounts and first purchase amounts? Well, that's what these histograms here at the bottom reveal to us. The far left one is comparing the averages of each of those permuted data sets. The difference is when we compare the averages. The one on the far right looks at the discrepancy when we compare the medians for the different levels of income. So what we find is the value of the discrepancy in our data is something that chance alone is pretty readily available to help to kind of explain. We see a lot of permuted data sets that have bigger discrepancies here. And so to no surprise, when we go and look at the p-values, if we compare averages, the p-values if we can compare medians, the 95% confidence intervals all contain values for these p-values that are at least 0.05, indicating that there's no statistically significant relationship going on. Another example, if we compare the wallet share of these customers, what fraction of money are customers spending on like purchases at this particular store? We do see from the box plots actually a pretty substantial relationship. The higher the income, the higher the wallet share. And if we were to go and compare averages, observe the discrepancy in those averages here, we find that, okay, there's a pretty big variation in those averages. The variation in those averages is about 20 times higher than we would expect by chance alone. And if we were to go and look at the values of this statistic, the discrepancy across all these permuted data sets where we randomly paired the wallet share with the customer's income, we find that those chance values of the discrepancy are typically a lot lower than what we observed in the data, regardless if we're comparing averages or if we're comparing medians. So what we observed in the data is so out of whack with what could have been produced by random chance that we're pretty convinced there's a statistically significant association. And looking at the estimated p-value, we find that the 95% confidence intervals for them all contain values less than 0.05. Yeah, this is a statistically significant association. And so finally, to numeric variables, if we're looking at the association between customer lifetime value, the total amount of money they spent at a store, versus their first purchase amount, we see the scatter plot's well described by a tilted rectangular band, a minor outlier, which is okay. So we can use Pearson's correlation to describe the strength of the relationship and to do the statistical testing. We observe a value of the correlation of about 0.24 here. Could this have been produced just by random chance when there's no association going on? Well, in the permutation procedure, we measure the correlations for those permuted data sets, randomly pairing together the x and y values, and we find that the correlations don't really get that far from zero, maybe up to 0.1, maybe down to minus 0.1. Our observed value of 0.2375 is pretty much out of whack with what could be expected to be produced just by chance alone, indicating that it looks like we have a statistically significant association. And in fact, if we look at the p-values, that pretty much confirms it. We find that the range of p-values we've nailed it down to with the permutation procedure, all less than 0.05. So yes, we have a statistically significant association. In analytics, very often we end up studying the associations between two numeric variables. So for